Hello, welcome back. We're doing video 3 of 3 for lesson number 3. So there's a lot of threes there. In this video, we're going to talk about the average rate of change and the instantaneous rate of change. And you guys can see that in these nice bold underlined letters. We're going to briefly talk about the average velocity and the instantaneous velocity as well. We go into that a lot more when we talk about particle motion. So I'm going to just highlight it here and give you guys just a little bit of information on those two things. And then we'll hit it hard for particle motion. And then I'd like to revisit the definition of the derivative that we talked about in the first video for this lesson and show you guys how to do some problems a little bit different than what we did in that very first video. So let's continue with our average rate of change, which I will always abbreviate as AROC. Why write all this out when we know that this is just AROC? And in this particular example, you've learned this as the slope of the secant line. Okay, so this is the slope of the secant line. I want to just say in just really layman's terms for this, right now average rate of change is going to be just f of b minus f of a all over b minus a. Okay, that's really what this is the slope of the secant line. So it's a slope. The instantaneous rate of change is going to be very similar to the definition of the derivative. The definition of derivative we talked again in video 1. I'm going to re-talk about that in this video here. So this is going to be the instantaneous rate of change. And so when you learn what a derivative is, it's going to basically say that when you find that derivative at this value c, the value that you get for this is going to be the instantaneous rate of change. What I like to do before I go on any further is just relate this to real life examples for you guys to understand. So again, I abbreviate this IROC. So when I talk about the mean value theorem, I use this example, so I might as well just use it earlier in this course. So what does it really mean, average rate of change, instantaneous rate of change? Because yeah, this is the slope of the secant line, this is the slope of the tangent line, but how do we do it in calculus? What does this mean? So I always use the analogy that we're leaving school on a field trip and we're heading to DC, right? We're heading to good old DC up here, and here's our little school, and we're driving on 66, right? We're leaving 66. And so we're going to be on, let's say, 66 for about 25 miles. So there's a 25-mile span from our school to the DC border, right? So let's say that we look every minute at our speedometer and we see what our speed is, okay? And so we start marking them all down. So every minute we look at our speed. We're at 60 miles per hour. We're at 63 miles per hour. We're at 65 miles per hour, 62, yada, yada, yada. We add all those up and we average. Let's say that on this road we average 63 miles per hour. And I now realize that that's probably not the best number because the speed limit on that road is 55, but no one really goes 55, right? So 63 is actually still pretty slow for this road. So I'm getting sidetracked. So the average rate of change of our drive from our school to DC is 63 miles per hour. So that was the average. The instantaneous rate of change. So let's say that we found that f prime of 7 is equal to 63. What does this mean? This means that at minute 7, we were going the exact speed that our average rate of change was, right? So that's what this is. So instantaneous rate of change is the time that we're doing, what is exactly what we're doing at that time? Like, what is the official time for this? I could also say that f prime of 9 is equal to 67 miles per hour. So that just simply means that time in the 9th minute, our car was going 67 miles per hour. That's all instantaneous rate of change is. The average rate of change, again, is the summation of them. Sorry, not the summation. The average of them, and the instantaneous rate of change is, okay, what's happening at that exact time? All right, so that's the idea behind those. And now we're going to look at the average velocity and the instantaneous velocity. You guys can see that average velocity is the same thing as the average rate of change. I tell students that they both begin with the word average. We do want to be careful because we do have something called the average value, which we'll get to much later in the course. But again, if you find the average velocity, again, I'm going to get a little kind of into particle motion here, as I said to you guys before. So if I'm looking at the position of something, The derivative of our position is going to be equal to velocity, and like I said, we'll get into this more so in our particle motion thing. So if I'm asked you guys to find the average velocity, the only reason that I'm talking about it right now is because students always mess this up, and I want to make sure that you guys are really clear with this. The average velocity is just going to be the slope of your position function. So when you're finding the average velocity, you are literally plugging it back into the position function. And the reason why is that when you find the slope of your position, you're actually getting the derivative, quote unquote, the derivative of your function, which is your velocity. Okay, so I know that may not make the most sense right this second. When we get to particle motion, I'm going to kind of hit that harder and make sure that you guys understand it. And so for the instantaneous velocity, again, that's happening. That's telling you what are we doing right now? What's our velocity at a particular time frame? All right, so that's all I kind of want to say about that. Let's move on down here to some examples and see what we can do with these particular problems. So for question number 4 and 5, it says find the particle whose position is. So I'll be honest with you guys, f of t is great. I like, and I'm going to use this a lot in my class, I like position to be s of t. So I'm going to go ahead and just really quickly write this as s of t because I know myself, and when I start doing these examples, I'm going to use s instead of f. So I'm going to go ahead and just rewrite it like this. You will see that a lot of calculus teachers and books also like x of t. It doesn't matter, and I don't care which one you use. As long as you get the right answer, I don't care which one you do. I like s for some reason, so that's the one I'm going to use. So it's asking us to find the average velocity of our function. Well, again, we're given the position function, which I'm going to relate this again to s. So average velocity, as soon as I see this, what I tell students to do, just as a good strategy, is go and say, oh, that's right, they just want the slope. They want the slope of my position function, because the slope of position actually gives you velocity. So that's why we do that. So I just got to find what s of 4 is, and I know that that's going to be 81. I know that, and I just looked at the answer, so don't think that I did that in my head really quickly. I'm not going to lie. And this is going to be 3, right? So s of 4 is 81. S of 1 is equal to 3. So my answer for this problem is going to be 81 minus 3 all over 3. And that's going to give us a value of 26 feet, right? 26 feet. So our average velocity is going to be 26 feet per whatever time frame that we're doing, all right? So whatever time we're looking at, right? So at time equals t. And so for question number 2, you do the exact same thing. It's just solidifying that it's just the slope of the position function, and that's all we're doing. So again, I say average velocity is slope of position. I'm going to keep saying it over and over and over. So s of 2 is equal to 17. We've already found what s of 1 is, right there at 3. So we're just going to go ahead and plug in. We're going to get plugging and chugging. We're going to get 17 minus 3 over 2 minus 1 is equal to 14 feet per second, whatever that is going to be. Or whatever time it is, I should say. So per time, but whatever it is. So this is our actual units for this. So let me actually fix that per second or time or hour or whatever we're doing. All right, so that's the average velocity. Guys, it's super simple. It's going to be the slope of your position function. And as I move further to the course, students always say, oh, velocity, you got to find the derivative. No, we do not. All right. For the last example here, it says find the instantaneous velocity at the particle time equals 1 second. So right now, I'm going to use the definition of the derivative because we technically haven't learned the derivative yet. We learned that in the very next video, so we're finally there. But since I'm giving you guys a time, and so this, I encourage you guys, if this doesn't make sense to you, go back and look at lesson 3, video 1. And I talk about it, the very first example, I'll do this. So I talk about the definition of the derivative. If we know the value of our function, right? And actually, let me do this. Let's be consistent with what I've done before. So I'm going to go ahead and just show you guys the formula that I used in the first video, and we can just modify it, to what we do here. So here it is. It's just going to be the average rate of change. We're going to add the limit right here to get the equation of our tangent line. And so all we need to solve these problems is, well, that c is clearly 1, right? So c is going to be 1. I know what f of x is. Well, f of x is really just the x of t, so these are just going to be x's. And then f of c, which is really f of c, is really just f of 1, and we know what f of 1 is right here. It's 3. So I apologize if the lettering's confusing you guys, but I just feel more comfortable giving you guys this equation based on how I taught it to you guys in the first lesson. And I know you guys are smart enough to realize that it doesn't matter what the letters are. They're the same thing. I know you guys know that this could be S, S. It doesn't really matter, right? So let's look at this with the limit as x approaches 1. So f of x is going to be what you guys see right here. It's just going to be 6x squared minus 4x plus 1. Minus f of c, which is f of 1, so that's going to be minus 3, and it's going to be all over x minus 1. All right, guys, just to save some time, we're going to just realize that if we were to plug in 1 to the top and to the bottom, we would get 0 over 0, so it's an indeterminate. We also would realize that we would combine this, and this would be a negative 2 here. We would factor out a 2, all right? We'd factor out a 2 here, and so we would get this as our factored form. I know you guys know how to factor, so I'm not showing every single step for this particular problem, but it's an indeterminate problem, so we use algebra. Well, clearly factoring is our best option here. We go ahead and we look at this problem, and we cancel out the x minus 1s, and so we're left with the limit as x approaches 1 of 2 times 3x plus 1, and then we just do substitution, right? We do 3 times 1 is 3 plus 1 is 4 is 8, and then be 8 feet per second, right? Okay, so average rate of change and average velocity, pretty much the same thing. Instantaneous velocity is, again, the instantaneous rate of change. So let us now look. We're going to look at these last examples right here, and this is very confusing for students, but it says for each of the following is a derivative, right? So we're saying it's a derivative. So basically they're giving us that these are the definition of the derivative. What is the function and what is the value? All right, or sorry, what is the function and at what point is it? So ladies and gentlemen, students may hate the definition of the derivative, but these are questions are on the AB and the BC exam. So looking at this, you should be able to do these problems really quickly without having to worry about algebra manipulation. Like this one right here, we don't really know what to do for this. Like, how can I factor that? Right? So, and this is going to be 0 over 0. So what would I do? I don't want to cube this. I don't want to do all that, right? So what's some strategy that we can do? So it's actually pretty basic if you know your definitions of your derivatives. So we're going to start with the one that I just did an example of. And so I want you guys to see this, and we're just going to go through these problems, and you're going to see how simple this is going to be. So we're now taking into account instantaneous rate of change. This is really what these problems are. Is that if I look at this is the instantaneous rate of change at time equals c. Well, I have three examples here where my value is an actual number. So notice for all the rest of them, they're all 0. So that's going to be the other one. That's going to be the other one we're going to get to here in a second. So if I'm looking at this particular example, then I know that my c in this case here is 2. So remember that the function is sitting right out front for you. So I know that the function has to be right in front of the number, the last number here. So I know that f of x is equal to x squared. Now I can verify that this is correct because I know that f of c, which is f of 2, right, part of this equation right here, that's going to be equal to 4. And lo and behold, it's right there. So I know that this function is f of x, and then my value here is 2. So what this question is asking us is what is f prime of 2? Because again, it is a derivative, f prime of 2. So you would plug in 2 to your function, right? Well, you'd have to take the derivative of this right here and then plug it in here. So I'm getting a little ahead of myself with this problem, but you would have to plug in the derivative to this, and you're going to get that this answer is 4. But the question is just asking us what's the function and at what point. So let me just stick with what that is. Sometimes I like to get ahead of myself quite a bit, so I do apologize for this. All right, for the next one right here, you can see that this is 3, so I know that c is equal to 3. Now, you may think, okay, well, x cubed is my function. Well, clearly not, because when I plug in 3 to this, I get 27, and that's not it. So again, using some common sense, our function f of x is literally written right there for us. And then again, you'd find the derivative of our function, and I'm going to just really quickly write that one out for us. It's going to be 3x squared plus 1. You guys will learn this in the next video. And then you're going to plug in 3. So you're going to plug in 3 to this function, and you're going to get that this is 28. Right, 28. So that means that this limit here is going to be equal to 28. So that's a really easy way of doing this. And again, we were able to do that because we knew the definition of the derivative. So students always ask, why we got to find that when we can use derivatives? It's because of problems like this. And then our last problem over here, we know that c is equal to 3. We know that our function, our f of x, is going to be equal to 2 over x. And again, ladies and gentlemen, we're looking to find f prime of 3. And so we'd find the derivative of this, which is very easy to do. Again, video 4, or example, lesson 4, we got you. And then you're going to find the function. So once you find the derivative of this and you plug in 3, that's going to give you the value of this limit. There's nothing else you need to do. You don't have to. So all that crazy stuff that we just did, because we talked about this problem before, where we get our common denominator, right? We do all that algebra skills. If you know your definition of the derivative, then you can simply go to this step right here. So it's kind of like a nice little tool for us to do to solve a limit much, much faster than what you guys have been doing algebraically. Okay, so you kind of choose your own poison and which one you like, which one you don't like. Do you like the definition of derivative, or do you want to do the whole algebra skill thing? Right, so that's the kind of idea for these problems. The other one that we're going to use here is the other definition of the derivative, which is the limit. And notice that these are all delta x's. I'm going to go ahead and being consistent with what I've done here. So I just want to, write down, it doesn't really matter if it's delta x or h. If you guys, it's the same thing here. So notice that in this particular example for these problems, all that you have to do is this. Okay, all you have to do is, so technically you see that these are all numbers. Well, that doesn't make any sense. Well, they've already put in the value. They've already put in what the value is for this, because we're asking at what point. So this is what you're going to do. So for example A, you're going to see 4 plus delta x squared, right? So you already know that 4 is the x, right? If you look at this problem right here, 4 is the x. So this, in case here, 4 or x is equal to c. And so you now know that, and this is what I always tell students to do, is now once you found out what c is, anytime you see a parentheses that's got a delta x or an h in it, go ahead and put a big ol' x in it, and that means that your function is going to be x, this big ol' x, squared. And again, ladies and gentlemen, you can check your work based on what we did in the first 3, is that if you plug in 4 here, you're going to get this value with what's going on here. So for this value, you would find the derivative of this function, which is going to be 2x, and you're going to plug in 4. So this derivative is equal to 8, or this limit is equal to 8 because of the definition of the derivative. So let's look at example number B, C, and F, and I'm going to go a lot faster now. So for this one, I'm going to go ahead and say, okay, well, there's clearly a 5 here, right? There's a 5 here, so this one's actually really easy to talk about. So the C is 5. And then once I've done that, I'm going to put a big old X here, and so I'm going to just write down what I see. So f of x is going to be equal to, don't forget our 2, and then this is x cubed, and there's our function. There's our function. And then we take the derivative of this, we plug in 5, and then we'd be really good to go for that particular example. So if we move on to our last two, we see that we have our x is right here, pi over 4. And then our function, so once I see that, I put a big old x everywhere I see a parentheses, so it's just cosine of x. And again, ladies and gentlemen, I know that I'm right. You know that you're right, because if you plug in cosine, sorry, this should be cosine of x, my apologies. I knew it in my head, wasn't going to tell you. So cosine of x, and so when you put in cosine of pi over 4, you get the square root of 2 over 2, so you know you're right. So the derivative of cosine is negative sine, plug in pi over 4, you get your value. And the last one here, hopefully you guys are getting it now. So you can see that I've got a 3 here, I've got a 3 here. And so I know that c is equal to 3. Whatever my function is, if I plug in 3 to the function, I better get 15. That's how I know I'm right. Well, again, everywhere you see parentheses, very easy, parentheses, parentheses, and then write what you see. Well, there's an x squared, and then plus 2x. And if you plug in 3 here, you get 3 squared is 9, plus 3 times 2 is 6, 9 plus 6 is 15. So that's all I have to say about this video. we're officially done with lesson number 3. Hopefully these videos helped you guys out, and we'll see you guys in the next video when we talk about derivatives.